All right, here we are back again for the this is hyperbola, the locus definition. So I think this is the last of the locus stuff. I'm going to move on to some other types of equations next lesson. So hyperbola. Here is the locus description. A hyperbola is the locus of a point P that moves so that the difference between the distances from two fixed points, F1 and F2, the foci is constant. So here's a thing here. And so here's our two foci, F1 and F2, and the distance there between focus 2 and point 2, that distance minus, because we're talking about difference, which is minus, minus that distance there is a constant. So here we put it like this. And we have I'll use the absolute values because distance doesn't have a direction, but that minus that is going to be a positive number because that one's bigger. But if we went the other way, this minus that would get a negative. However, that difference between the two would be the same. All right, so let's have a look. Consider the points 2, 0 and B is, negative 2, 0 and B, which is 2, 0. Find the equation of the locus of point P where, I should say, not when, where AP minus BP is 3. So that distance minus that distance is 3. And given that this is the long one, I don't need to worry about the magnitude. That's going to be taken into account because I've just taken the long one minus the short one. All right, so there's a bit of mucking around, and so we're using that distance formula again as we did before, and so we're starting with AP minus BP equals 3. So the distance formula, the square root of x minus negative 2 plus y minus 0, take BP, square root, x minus 2 plus y minus 0, and that is equal to 3. And so here we've got the same issue that we had before when we looked at last time at the ellipse, all right, where we got this minus in here, so we can't just square both sides to get rid of these. So again, we're going to do the same strategy we did before, move that across over there. So the square root of x plus 2 squared plus y squared is equal to 3 minus the square root of all of that. All right, now we can do our squaring of both sides. Remember, squaring is multiplying by itself twice. All right, so on the left-hand side, that just removes the square root and the squared. They are in opposites to each other, inverses, so they cancel. And here we've got 3 3s are 9, minus 3 times the square root, minus another 3 times the square root. Now, I've made a mistake there. Those that have hopefully picked that up, when I move that across over to here, we've got to add it to both sides. So that's a plus. So that's a plus 3 3s are 9, 3 times there, plus another 3, so plus, sorry about that. And then plus times a plus, so plus, again, that square root times that square root, so it just removes the square root. All right, expand, collect your like terms. So I've got on the left x squared plus 4x plus 4 plus y squared equals 9 plus 6 times the square root. Got a squared there. Plus x squared minus 4x plus 4 plus y squared. Collect some like terms. Well, if we take y squared from both sides, they go. If we take x squared from both sides, they go. I'm going to move this by adding 4x to both sides. So I'll get 8x. I take 4 from both sides, so they go there. And then I take 9 from both sides to move that. And then I've got 6 root x minus 2 squared plus y squared. All right, so now before we move on, I'm just going to point something out here. And that is, over here on the left-hand side, we've got an x, we take 2 and we square it. So whenever we square something, we end up with a positive number. We're adding y squared, so again, that's a positive number. So we're taking the square root of a positive number and then times it by positive 6. So our left-hand side here, or the right-hand side, so the right-hand side is going to be a positive number. So because this is an equation, this x here that we use has to fit in with the right-hand side being positive. Now, if the right-hand side is positive, then the left-hand side has to be positive as well. So that means the left-hand side has to be positive. So if you like, 8x minus 9 has to be greater than 0. And then when you rearrange that, x has got to be greater than 9/8. All right, now that kind of makes a little bit of sense when you think about up here. So you notice here in between our hyperbola, in the middle, we've got something that doesn't exist in the middle here. All right, so what we're talking about here is that x has got to be up there somewhere. Now, of course, there's a second arm as well, so technically speaking, to get that other arm, the magnitude of x, it's got to be greater than 9/8. All right, so we don't actually really need to, for our manipulations, we don't need to worry so much about that, but just a reminder, there's a gap in the middle here, so there are some x values that don't happen or don't occur, and those x values that don't occur are the ones where you would get a negative answer on this side but a positive answer on that side, which of course if they're equal doesn't work. Anyway, I've waffled on about that enough. So what do we need to do then? Well, from here we can square both sides straight away now. So we'll square both sides. So when we do that, you get that bracket by itself. And so when I square that bracket, I would get, I better write it out, 8x minus 9 squared. And this side here, I've got 36 times by x minus 2 squared plus y squared. All right, so expanding this, I get 64x squared. 9 8s are 72, and I get that twice, so I get minus 144x, and plus 81 equals 36 lots of x squared minus 4x plus 4 plus y squared. And so I've got 64x squared minus 144x plus 81, 3x squared minus 12x plus 12 plus 3y squared. All right, let's do some stuff here. So what I'm going to do is I'm going to put all the things with x and y onto the left and all the numbers to the right. So I've got 64x squared there, 3x squared. So I'm going to take it 3x squared. And so when I do that, oops, 36 became, lucky, oops, lucky I checked my notes there, isn't it? Transcribing error, 36 should be, so that's 36. 36 times 4 is 144. 144, 36. So I'm taking 36. 64 minus 36 is 28. You were to do that. So 28 x squared. Add 144x to both sides. Yeah, I've taken 36x squared. I've got to take 36y squared when I'm bringing that over. And then I've got to take 8. And when I bring it over there, 81. Oh, another transcription error. 81. Take 81. And then when you do 144 minus 81, you get 63. Oh. All right. Get too tired, I think. So hopefully those two transcription errors here haven't freaked you out too much. Okay, so what do we do then? Then we divide by 63. We do some cancelling here. All right, and 7 goes into each of those, so 4 and 9. And over here, 9 goes into both of those, and equals 1. All right, so there's our Cartesian equation of that particular thing with that locus. And you'll notice there's similarity here between this and the ellipse one, but we have minus here instead. All right, so sorry about those transcription errors, fixed them up in the end. And now let's move on. So Cartesian equation, there we go. An example above results in the Cartesian equation. So in general, with our Cartesian equation, x minus h squared on a squared minus y minus k squared on b squared equals 1. Minus here for hyperbola. So centre is h and k. Vertices, that's these bits here. H plus or minus a. So again, we move plus or minus a, moving that way, and k. And then we've got asymptotes for hyperbola. All right, so this is a different type of hyperbola than we've done perhaps in the past. We've done ones that are rectangular where we have asymptotes which are vertical and a horizontal. This is a different type, and so this has got the ones that are at an angle, and here's their equation based on stuff from here. All right. And the plus or minus, one of them's with the positive gradient, the other one's with the negative gradient. All right. So I've got a little bit more to go here. So let's have a look at an example of sketching a hyperbola from our Cartesian equation. So show the centre of the vertex, the asymptotes. So when we look at this one, h is 0, nothing there with that. So h is 0. K is with the y, and k is, in this case, is that -1? Excuse me, that's a +1. Is that a +1? No, it's a -1. It's a negative. Looks like a positive, so it's a -1. So k is 1. All right. Then a squared is 9, so a is 3, and b is 2. And so we use this information. So my centre is hk, so 0, 1. Our vertices are h plus or minus a, so 3, and k, which is 1. So we've got two vertices, one at -3, 0, and the other one at 3, 0. And we've got asymptotes. All right, so y minus k plus or minus b on a, x minus h. So y minus k plus or minus b on a, 2/3. Okay, no, b on a. Yep, b on a, 2/3. X minus h, which is 0. Sorry, a bit vague there. So y minus 1 equals plus or minus 2/3 x. Now move the 1 across by adding. So we've got 2, and one of them is negative gradient, -2/3 x plus 1, and the other one is positive gradient, so 2/3 x plus 1. All right, so let's have a little bit of a sketch of this. We've got a centre here at 1, 0, 1. Vertices, more transcription errors here. One. So -3, 1 and 3, 1. All right, 1, 2, 3, -3, 1. Let's say there. 1, 2, 3, 1. So there. That's the centre. All right, then we've got some asymptotes, and I'm going to change some colours to give me my asymptotes. And then I'm going to show you a bit of a trick on the asymptotes. Oh, hang on a second, I forgot my +1 here. All right, so let's change my colour, put my asymptotes in. All right, so here, -2/3 plus 1. So here the asymptotes, it starts at here, goes through y as 1. And this just happens to be, in this case, the centre, so you can always work off the centre. So here we're on -2 on 3, so rise over run. -2 is the rise, and the run is 3. So I go down 1, 2, and across 1, 2, 3 to there. And so one of my asymptotes goes there. Then for this one here, rise over run, +2, so up 2 and across 3 to there. And so this one goes like that. All right. And then our hyperbola, I'll change my colour back, fits in there. So if the vertex is here, it's got to go around like so. Got to go around like so. All right, so there we are. There's our hyperbola that we've got sketched there. All right, so a note here. So, all right, so up here, what we had here, so we had the x part minus the y part. Now, if we have it the other way around, the y part minus the x part, instead of the graph being, because remember this breaks into 4 bits, so instead of the graph being here, stretching in the x direction, when we've got it as the y part minus the x part, it stretches this way in the y direction here. And so we've got a little bit of a change in our centre and our vertices for those particular things. So if we're going to sketch this particular one, because it's the y minus the x, we've got some slight changes. So our centre, that doesn't change. That's still these numbers here, so -2 and 1. And of course the h is -2 and our k is 1. Our a is still associated with that, so our a is still 3, and our b is still associated with the y, and so that's 2. The bit that changes here is now our vertices. All right, so the vertices now stay on that x line, so they're staying on -2, but they're now our k plus or minus our b. Just remember, this stretches up this way, so we're stretching 2 up that way. So our vertices are -2 and -1. So 1 minus 2 and -2 and 3, 1 plus. All right, our asymptotes, well, it doesn't change. It's only our vertices bits that change, our asymptotes. All right, so they're still in the same position. So it's y minus the 1 equals plus or minus b on a, so 2/3 of x minus 2, so x plus 2. All right, and so you can then rearrange those. So one of them is the y minus 1 equaling the 2/3 x plus 2, and that one, oops, in there, and that becomes 2/3 x plus 7/3, and the other one is y minus 1 equals the -2/3 x plus 2, and when you rearrange that one, you get -2/3 x minus 1/3. All right, so we've got all that we need. And oops, I forgot the x in there. We've got all that we need. All right. So let me draw it in here. So very rough here. All right, so centre, start with your centre, and the centre is at -2 and 1. So our centre, -2 and 1, there it is. Vertices, 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 vertices. I've got one at -2 and -1. So I've got a vertex down here. And the other one is -2 and 3. Yes, -2 and 3. All right, 1, 2, and 3. And then we've got some asymptotes. All right, so now we've got these two. Now, I kind of use that, what I showed you before. You can use that again. So rather than trying to figure out roughly where this is here and roughly where that is, you can work it off your center, because the asymptotes go through the center and they have this gradient. So yes, this is the gradient y-intercept form, but because the y-intercept is fraction, it makes it a bit more tricky. But what we know is 2/3 is the gradient. So if we were to then say, okay, 2/3 is my gradient, excuse me, 2/3 is my gradient, so a rise of 1, 2 and a run of 1, 2, 3, then this one goes through there like so. And the other one had the -2/3 gradient, so we go down 1, 2 and a run of 1, 2, 3, and so that one goes like this. All right, and so that one's the 2/3 x plus the 7 on 3, and this one here is the -2/3 x minus the 1/3. All right, so that saves us having to try and find where these are and work off that. All right, so then when I go back and I change my color back, here's my vertexes, so I know it goes like so and like so. And you could work out intercepts if you wanted to. All right, so there's our hyperbola. All right, now one of the things that we didn't talk about at all, I'm going to now, was the things at the front. Was at the first part I said conics. So I haven't actually mentioned about conics, but what we've been doing for the last bit when we've been doing the locus is what we call conics or conic sections. So that's another name of these things. So here are conic sections. So circles, ellipses, parabolas, hyperbolas are known as conic sections. And how does that get? Well, if two cones are balanced on their points and cut in particular ways, the shapes of the cross section are that of these graphs. So here's our couple of cones. So we've got two cones on our points. And so if you put a line down, straight down the middle through that, and then you put another line that's at 90 degrees, and you have a look, that section that's there is a circle. If you put that line at an angle rather than at right angles, then that section, cross section you get is an ellipse. For your parabola, so we're cutting along this line, we're cutting along this line. So for your parabola, if this edge here of our cones, if we cut parallel to that, then that shape that you get there is a parabola. And for hyperbolas, if you cut down through your cones, and so this one's vertical cut, this one's at a little bit of an angle, but it doesn't matter as long as it cuts as long as the line cuts both cones, then that shape you get in there is your hyperbola. So you might also hear these things called as conic sections of cones when you cut them. That's all I'm going to mention about that conic section stuff. It's just to point out what they're about as well. All right, so that's it for the locus description of things and the hyperbola. If you need some assistance with any of that, make sure you yell out for it. And as always, have fun.